Okay, so good morning, everyone. So today we will present you the Xen-based ARM autonomy stack using Yocto. My name is Bertrand Marquis, and I am a principal software engineer at ARM in the open source software group. I am working on the Yocto autonomy reference stack that I will present today, but I am also working on Xen on ARM. I will be presenting today with John Mason. John, I will let you introduce yourself.
Sure.
John.
So I'm John Mason. I also work at ARM, I guess indirectly with Bertrand. I'm kind of the principal Yocto developer at ARM. There are many other Yocto developers inside ARM, but I kind of help corral them and focus them upstream. I'm the principal maintainer of MetaArm open embedded layer, and I'm also an open embedded board member.
So today we will start the presentation by explaining you why ARM is creating the autonomy reference stack and what it is exactly. We'll then detail the work of ARM on Yocto with the MetaArm layer and how this is used for the reference stack. And finally, we will give you a status update on the current implementation and what can be expected in the future. So first, why is ARM creating a Xen autonomy reference stack? So autonomy systems are very complex. That's systems like self-driving cars, but also robots. A self-driving car includes complex input processing, like video or LiDAR, number of computation going from artificial intelligence to voice recognition, and several output handling. That's managing the engine, but that can also be playing music on Android Auto. An hypervisor can make development easier by splitting the system in different components. Each one can be implemented by different groups or companies. It can be used as a generic platform to have functions developed independently of the hardware and reused on different systems. It can also make development easier by isolating critical from non-critical parts, reducing certification costs, giving more control on the boot flow, or allowing independent update management of different functions. So why choosing Xen? So first, Xen is a type 1 hypervisor, means it does not need a rich OS as host. This is reducing the amount of critical code and enable faster boot time to critical functions in comparison to what you could do with a type 2 hypervisor. Xen is open source and has a wide community of users and developers. It is used in a number of servers and applications, and Xen community is pushing towards embedded systems. FUSA project is looking at the Xen certification, while several industry leaders like ARM want to help Xen being more suitable for embedded systems. For example, there is a Xen automotive group that you can find on Xen website. With the autonomy reference stack, we want to create a Xen-based stack suitable for autonomy systems. The stack will focus on boot time and strip functionality to be suitable for embedded systems. The stack will provide a small and simple way to manage guests, from how to start and stop Xen to a deployment system suitable for embedded application. The stack will include features focusing on safety and security, like opt-in integration, secure boot, or update problematic. And finally, the stack will provide an easy way to integrate different components and have guests usable on different systems. This slide shows the blocks of a system based on the autonomy reference stack. All components in light blue are the focus or will be the focus of the stack. So first, you have a firmware based on trusted firmware from ARM and Opti. You have the Xen hypervisor, a DOM0 Linux with tools to manage guests, and then guests based on Linux, but those could be also based on other RTOS. And those guests will contain the actual workloads of the system. So I will let John handle the Yocto part.
In the previous slide, you saw talking about a reference stack, but how do we build a custom reference stack? And the easiest way is with Yocto. So the Yocto project is a set of templates, tools, and methods that help you build custom-based Linux systems. So if you're looking over to the right, you might see kind of a bit of an eye chart of different pieces interlocking together, and it might be quite confusing. But the pieces that I want you to kind of focus on here are in the lower right-hand corner. You'll see images, and essentially this is the process of how images are created. And over to the left of the infographic is a, I guess this is an infographic, but a graphic, is the layer piece. So what you'll see are how these pieces all pull together, and also kind of notice up in the upper portion of it, the source code and the source mirrors and how it's being fetched down. So this is, I don't want to dig too deep into the details of Yocto and how it's happening. So hopefully everyone has at least a rough understanding of Yocto. And yeah. So the MetaArm layer. So essentially, we've created the layering aspect that from the previous page, and this is kind of how it's made up. So you have your own custom Linux distribution to the right and the left, and each of these is done by layers. And the layers are made up of individual pieces. It's meant to be highly modular. So each of these layers is made up of recipes. And if you look down at the pieces, you'll notice that some of these are duplicated from the right and the left. And what that's meant to show is kind of common dependencies. So the dark blue on the left, you'll see MetaArm BSP, and in the right, you'll see the red and MetaArm Xilinx, for example. And what this is meant to show is that you can easily remove a piece and replace it with another that has the same dependencies, and that's the kind of modularity that Yocto has. And also you have the side-by-side pieces that make up your custom distribution. So for example, in it, you're going to need a kernel, and the kernel will be made up of, will come from the MetaArm BSP, and that'll be applying patches on top of MetaArm. So that's what this graphic is meant to show. So why do we go through this effort of making a custom layer, which we are calling MetaArm? Well, unfortunately, there are many ARM, well, fortunately, there are many ARM vendors. Unfortunately, they're kind of doing their own thing. So we have each one doing their own unique Yocto layer, making divergent recipes for things like kernel and U-boot. And each one is a different version of Yocto. And because everyone's doing their own thing, there's no intrinsic need to upstream. They're just pushing random, or not everyone, but some are pushing random Git trees to GitHub, for example, with just their changes on top of a snapshotted tree. And this creates a large problem because it makes it difficult to upgrade to new versions of Yocto and the underlying software. And by this, I mean, in later this month, a new version of Yocto will be coming out, Dunfell, I believe it's named. And if you were 3 versions behind, snapshotted to all this stuff, it's almost impossible to force an upgrade, or it's not impossible, it's extremely difficult, a lot of hours to put in that's unnecessary. So, and because of that, there's no shared work because everyone's doing their own thing. And because everyone's doing their own thing, you don't know how well each layer and each recipe is tested. And the kind of final nail in the coffin is that they're often not following the ARM recommended processes or implementations. For example, ARM would really, really love for everyone, all the ARM BSPs to be running secure boot and Opti, so we can have the highest level of trust and security. And because there's no shared work, a lot of these vendors will just get it working and throw it over the fence. So MetaArm is intended to be the one-stop shop for all of ARM software. Kind of to answer all those problems on the previous slide, where we're making it, we're pulling in all the ARM specific software, all the reference hardware and the BSP enablements, the tool chains, the autonomy, and maybe even some distro reference distros. Also, this is intended on being a place to collaborate so that ARM vendors can, from 2 slides ago, can take the pieces they care about for MetaArm and use that in their own reference layers or meta layers. So for example, MetaXilinx can take the trusted firmware recipe and just apply their stuff on top and not need to maintain the core of it, just their own unique piece of it. And because of it all being a single place, we can run CI, continuous integration on it constantly, so we have stability and quality in it. And I think most importantly for me, we want ARM to model the behavior for all ARM platforms, and hopefully all vendors see it and see it as a good thing and just copy the relevant pieces so they don't need to do the work. And that's that'll save a lot of effort on everyone's plate there. So MetaArm is made up of a bunch of different pieces, and most confusingly, we have MetaArm. So the confusing part here is that MetaArm is a collection of layers, and inside that we have the core pieces of layers, which we are calling MetaArm. So these are kind of the generic recipes. For example, the trusted firmware A recipes, the Opt recipes, and recently we pulled in something called OpenSCD support. So this is really just kind of the core pieces that other layers will want to reference. And MetaArm BSP. So I'm sure many people out there have heard of the Juno board. This layer will provide basic support. There's already support out there in the Linaro layers, but because this is ARM reference hardware, we should be the best ones to support it, and so we've had many communications with the people working on Yocto inside Linaro, and we're transitioning to MetaArm. In addition to that, we have the software foundation models, also known as FEP, which enables you in software to model the ARM references or ARM designs, and enables you to test it 100% in software. And we also have some hardware platforms, and more will be added to that in the future. And then we also have MetaArm toolchain. So Linaro people will probably remember the ARM or the Linaro binary toolchains and software toolchains that they've been developing for years and years and years. In the past year or two, that has been transitioned to transitioned to be supported by ARM. And ARM is every year, I believe twice a year, releasing software releases of GCC and binary versions of the same GCC tool chains. They are currently 8.2, 8.3, and 9.2. And in this layer, you can easily add these to be used inside your Yocto layers.
So the MetaArm autonomy is another sublayer present in MetaArm, and is an implementation of the reference stack I presented earlier based on Yocto. So it can be used to build all components of the stack, from the firmware, Xen, and DOM0 to guests. This layer can be used with other layers to use external BSPs, recipes, or workloads like AGL or waylanding guests. It is designed to be easy to use and suitable for fast prototyping and research. The first part of the autonomy stack is building the host system with the firmware, Xen, and the DOM0 Linux. So Xen is built based on the meta virtualization recipe, which are already existing. The layer is also providing a way to build a Xen-compatible device tree created from an existing DTB, but adding the parts required to boot Xen and DOM0 Linux on top of Xen. A DOM0 Linux is built with Xen backend drivers and required tools in the root file system to manage the guests. So this is implemented as a Yocto distribution feature named ARM Autonomy Host. The layer also provides an image named ARM Autonomy Host Image Minimal to create a minimal DOM0 system with all required tools to manage Xen guests. The second part of the autonomy stack is building guests. The layer provides a Yocto distribution named ARM Autonomy Guest for that. The feature will add Xen front-end drivers in Linux kernel and some customization to be able to run as guests, that, for example, having the console on HVC Xeon. There is no specific image provided for guests, as the feature can be used with any existing Yocto image. So it can be tried with the Yocto core image minimal, for example. The layer also provides a BSP named ARM64 Autonomy Guest. This BSP provides a minimal kernel configuration suitable to run as a Xen guest. It can be used to generate platform-independent guests, only relying on Xen front-end drivers for communication. The MetaArm autonomy layer is introducing the Xen guest system. This is a minimal Xen guest image and management system. A Xen guest image will include all components required to build a Xen guest. So that's the kernel, the device tree, but also the configuration, a definition of the disk and its content, and some initialization scripts that will be run on the host when starting the guest. The Xen guest MK image tool is used to manipulate such images. So that's creating or modifying them, but also extracting them. And the tool can be used on both your host development system and on the target. The Xen guest manager is a tool to be used in the DOM0 system to manage Xen guest based on the Xen guest images. So the manager will start and stop your guest. And it can also use LVM to create disks for the guest based on the configuration they include. It also provides an init support so that your guests are starting automatically on boot. So the Xen guest system is integrated in Yocto with several components. The first one is a file system type, which is used to create a full Xen guest image when you build a Yocto image. So that includes the root file system and the kernel, but also the Xen configuration. We provide a class named Xen guest image extra that can be used in recipes to extend this image. That's, for example, providing an init script so that you can customize your guest when you start it. The Xen guest manager is included on the host image to manage guests created with this. We also provide a network bridge system, which will create a bridge on the DOM0 to which guests can connect so that they have connectivity to the external world using network. So the layer will include lots of parameters so that each of those components can actually be customized, from what amount of RAM you want to the guest to what this partition should be used to create LVM volumes. So let's conclude today's presentation by giving you a status and what you can expect from MetaArm in the future. So first, MetaArm was deployed in January 2020 in the Git Yocto project, and the first feedback we had is very promising. First beta of MetaArm autonomy has been pushed to MetaArm mailing list last week and should be merged shortly. We will release our first stable version with Yocto Dunfell in April. In the future, we will add more BSPs to MetaArm BSPs. So that's, for example, one for Core Stone 700 or for the N1 SDP board. We will add more software support to MetaArm. So there are plans for an EDK2 recipe or an SCP recipe. And we will continue to enhance MetaArm autonomy, optimizing the boot time, the size, managing security, including OPTI, make development easier for everyone, and add compatibility with other layers, for example, with AGI. So for more information, please go to the Yocto project documentation. You can clone and use our layer, and you can join our mailing list if you need help or if you want to contribute to MetaArm. Thanks, everyone. So if you have questions, I think we can answer them now. Okay. So, Paul, in all this stuff described, well, that's, I guess, for the previous presentation.
Yes, I'm not sure we've had any questions. Oh, there we go.
Okay. What is the difference between DOM-U and DOM-0? That's a question from Drew. Well, DOM-0 is the part in Xen creating guests. A DOM-U is a guest which has in Xen naming scheme, that's just a guest which has no access to any hardware devices. So it's only relying on Xen drivers to have access to stuff like disks or Ethernet. So it's only using virtual drivers. So Peng's questions. How to secure boot for a DOM-U. So the idea is to handle this part from the DOM-0. So DOM-0 will be secure boot. And in the chain of trust, DOM-0 will actually check the image, including the kernel, the file system, and all components before starting a guest. So you build a chain of trust. DOM-0 is trusted, then as DOM-0 is trusted, it can check the guests before starting them. So then we have wrong window. Okay, anyone else has question? File system checking can be time consuming. Yes, it can. That's why we have to do some research on this. So the initial file system can be checked, but then if you have checked the initial file system and you let your guest run and you check only the parts that you update, you might be able to handle some updates in a fast way. But definitely, yes, I agree that can be time consuming, but it will be application dependent. Maybe you will not need to check it. What platforms qualify for being in MetaArm instead of Meta vendor like MetaFSL or MetaTI? I guess this is more a question for John. John, do you want to answer this one?
So sure. So this isn't intended on taking from Meta vendor, for example. This is intended to supplement it. So for example, you talked about MetaTI. So what we'd like is for MetaTI to be dependent in the parlance of Yocto and Open Embedded. We like it to be dependent. So it would pull the recipe for trusted firmware from MetaArm, and then inside its BSP portion, it would augment that recipe through a BB append and, for example, overwrite where the source is coming from, and then use that BB append to build their specific TFA recipes.
So on this question, MetaArm BSP itself is supposed to be the place to all BSPs for ARM produced systems. So that's more emulators like FVP, Juno boards as a development board that you can get from ARM directly. It's not supposed to hold any BSP from vendors like Xilinx or NXP or Renesas, for example. Those vendors will use MetaArm to retrieve the trusted firmware recipe, but will not use MetaArm to put their own BSPs. That's not the aim of the layer.
Yeah, and hopefully very soon. I've been in contact with some people at Xilinx, and they're very interested in using our TFA recipe in their layer.
So from YouTube, Charlie asked what percentage of the target system resource is used needed for the Xen framework infrastructure. That's not something I cannot answer to that because it's a lot more complex than just giving a number. Depending on what you do, it can be down to 0% if your guest does not require any communication with the DOM0, then there will be almost no overhead, apart from the overhead introduced by hardware virtualization, like second level of page tables is introducing an overhead. But there is no definitive answer to that. It's not possible to give a percentage of overhead. Sorry. Any other question?
I think we're there. Thank you, Bertrand and John, for your session.
Thank you, everyone.